Hello, today we're in the 9CI RF testing lab and we're here to learn the basics of pulsed digital modulation. And you might be surprised at how it all started. In order to demonstrate how this works in the real world, we're going to use real RF test equipment. Shown here is a signal generator. And this particular unit is capable of generating radio frequency signals at highly accurate power levels from 10 megahertz to 20 gigahertz. Today's tests will happen at 200 megahertz. And there's a few reasons for that. It's a convenient frequency to display on the oscilloscope. And it's also a frequency that's convenient for the Safe and Sound Pro 2 RF meter to show. So the signal generator, think of it as think of the signal generator as a multifunction radio transmitter. It's capable of transmitting all kinds of different modulation techniques depending on what signals I patch into different inputs. So today we're going to demonstrate pulse digital, but before I'll just show you a little bit of amplitude modulation, one of the earliest forms of modulation. The next piece of test equipment is the oscilloscope. And it's a device that graphically displays varying signal voltages, and its speed of displaying or its response time is called sweep time, and the amount of time for the scope to draw from here to here, it's called the sweep time, and we can vary that depending on the frequency of wave or signal that we want to monitor. The next thing in our demonstration will be a multifunction generator. Okay, and this is going to be set to generate simulate our digital sources. I've got it set to output square waves. In other words, waves that are either on or off. And I can vary this frequency. We're going to start at 20 hertz, but we'll vary it, and I'll show you what that looks like. And quickly, just to demonstrate amplitude modulation, I've got a mixer here, an audio preamp, a mixer, and microphone that I will patch into the signal generator to show what amplitude modulation looks like. So I'll get the camera set up so that we can see the oscilloscope screen, and let's go. Okay, to begin, we're going to show what a carrier or continuous wave signal looks like. All radio frequency transmitters are capable of generating CW signals, and whenever you hear me say the term CW, I'm talking about continuous wave. Okay? So if I turn on the signal generator, we see this white blotch on the scope here. Okay? So the power from the signal generator is coming into the scope, and then I've got it branched off to go behind into a dummy load antenna. It's called a 50 ohm termination load. And then we're leaking a little bit of RF so that the Safe and Sound Pro 2 can measure what's going on. So, notice the Safe and Sound Pro 2 is showing a constant level, okay? And I've got the speaker sound on here. There's an amplified speaker here, but I'm not hearing anything because there is no modulation. Now, if I zoom in or increase the sweep frequency of this scope, and I zoom in, what we're going to see, some of you might recognize this as a sine wave, okay? So, looking at the scope carefully, the distance between these peaks, or the period, is 5 nanoseconds, which translates to 200 megahertz. Okay, so the signal generator is generating just a pure sine wave, no different like in the audio frequencies, it would be a tuning fork ringing perfectly. Okay, so this is our carrier. Now on top of that carrier, we can do a bunch of things. We can modulate that carrier, we can turn it on and off, so we can modulate it with amplitude, AM modulation, or we can change the frequency slightly, a little bit shift it around, and we call that frequency modulation, which you're used to with FM radios. Okay, but today we're going to just show you I'm going to go back in time a little bit to the earliest days of digital and amplitude modulation. So let's zoom out in time here. And what I'm going to do now is take my voice in the microphone and, excuse me, I have to turn down the volume speaker. I'm going to amplitude modulate this signal. So right now, you are seeing my voice going to the audio amplifier and changing the transmitter power output based on the loudness of my voice. Okay, this was the first method that voice communications ever happened in the world. Now you'll notice as I'm talking, the peak levels go up quite high. I'm actually over-modulating a bit. Technically, I want to keep the modulation, 100% AM modulation within a certain range, but for the demonstration, I just want you to see what amplitude modulation looks like, okay? So essentially, if I was to put a microphone here to the speaker of the Safe and Sound Pro, I would be hearing my voice clearly through the speaker, okay? So that's amplitude modulation. Now, let's take this, I'm going to zoom out a little bit more, and let's now patch in a 20 hertz square wave signal. So what's going to happen is that this carrier is going to be turned on and off, full power, zero power, full power, zero power. It's going to be turned on and off 20 times per second. Now look at what we're seeing here. Okay, so this is a visual representation of the carrier being pulse modulated. Okay, so the term digital simply means that it's either a 1 or a 0, an on or an off. Okay, so in this period of time here, which happens to be, looks like each division here is 20 milliseconds, something like that. So we get full power on, then there's an equal amount of time where it's off, full power on, off. Okay, let's hear what that list sounds like. Okay, now what I'm going to do is increase that pulse modulation frequency. Let's step it up. Okay, so now that is 50 hertz modulation, and you can see that things got closer together, so there's more pulses in a given amount of time. Okay, so again, it's a signal that I can zoom in a little bit more so that we can represent these pulses. That's a nice thing about an oscilloscope. You can stretch or compress time to be able to take a closer look at things. Okay, so now we've got 100% power, 0 power, 100% power. But again, if I zoom in, I'm zooming into one of those pulses, we're still seeing this 200 megahertz carrier signal there. So within those pulses, you're pulsing, you're turning on and off this 200 megahertz transmitter to either full power or no power. Okay? Now what's interesting historically for this is the earliest days of Morse code. Never really thought about it before, but that could be considered one of the earliest times, one of the earliest experiences of really slow digital modulation, because whenever the Morse code key was pressed with an international Morse code standard that was established throughout the world for communications, you were keying the transmitter either on or off depending on the letter that you were sending. Okay, and so that is a form of digital communication. In the earliest days of transmitters, they actually used spark gap transmitters, which are very crude methods of generating RF. But as you know, when vacuum tubes were invented and stable oscillators and things like that, we could actually limit the transmitter to one frequency. So that's the earliest days of pulse digital. Now for the next part, what I'm going to do in modern digital communications, these pulses are extremely narrow. Okay, we're demonstrating very low frequency digital pulses, and the sounds that come out of the Safe and Sound Pro 2 speaker are sounds, they're demodulated sounds. In other words, the Safe and Sound Pro or RF meters, they just measure the carrier power, but what comes out of the speaker is just the audible pulses, the pulses that you can hear that are in the human hearing range. So we'll hear everything from, from a few hertz up to maybe 12 or 15 kilohertz through this little speaker. But modern high-speed digital pulses are very high frequency. They're in the hundreds of megahertz, or what's coming up with 5G, the pulses will be in the gigahertz range. So obviously we can't hear it, but they're there. And if we looked at a, with a fancy high-cost oscilloscope, we would actually be able to see these pulses. So what I'm going to demonstrate are single narrow pulses, and why it's important for an RF meter to be able to receive narrow pulses for high-speed digital communications. So I'll just get things set up for that and we'll carry on. Okay, we're set up now for generating single RF pulses. So we're not seeing a line on the scope right now because I've got the oscilloscope set to detect just single pulses. Okay? Now, oh, by the way, if it sounds like I'm shouting, it's because this RF signal generator that's to the right, the cooling fan is so loud in it that I feel like I'm shouting over it. So that's why it sounds like I'm talking in a lecture hall of hundreds of people. So right now I've got the function generator set. When I push this button, I'm going to generate a pulse that is exactly 50 microseconds wide. So here we go. I push the button, and there is our pulse. Now it's not entirely square wave. That can vary. That's the limitation of some analog connections, the quality of the cables going between the equipment and things like that. But as you can see right now, I've got, this is, in fact, I've got this set up for 20 microseconds. Each division shown on the scope is 10 microseconds, and I've got 2 divisions wide. So this is a 20 microsecond pulse. Let's do another one here. I'll put it in single capture mode, and okay, so that's looking a little better. But again, so nothing in time, and then all of a sudden the transmitter's at full power, but only for a very short amount of time. There are a lot of RF meters out there that cannot even measure 20 microsecond pulses. So let's go down now and take this down to a 5 microsecond pulse. And I'll set this up for a single capture again. And here's our single 5 microsecond pulse. Okay, notice how much narrower it is right now. Each block on the scope screen represents 10 microseconds, and we're half a block, so that's 5 microseconds. Okay, so that is a single narrow RF pulse. Now next we're going to be talking about, as I said, why it's important for an RF meter to be able to measure very narrow pulses, especially as high-speed digital communication speeds, bandwidths go up. All right, so the pulses are going to get narrower, and the more narrow a pulse that you can capture, the more accurate your reading on the screen will be. I just want to show you one more time with the 5 microsecond pulse. This time, take a look at the Safe and Sound Pro 2 when I actually do the trigger. Okay, so you saw it jump up a little bit there, and it actually measured that. And this meter actually, we've specified it for 5 microseconds, but it actually does well down to 3 microsecond pulses. So next, I'll talk a little bit about why it's important to have a meter that is capable of measuring in such narrow time spans. Okay, the idea of an RF meter is to accurately measure the amount of power that your body is receiving. Okay, and in this day with modern high-speed digital pulses, pulse frequency or pulse modulation, some of the pulses are very narrow. And so the better the meter is at detecting narrow pulses, the more accurate the reading will be. Okay, so what's happening in a modern RF meter is it's converting these analog signals into numbers that you can read on the screen. So that's called an analog to digital conversion. Okay, so in the case of the Safe and Sound Pro 2 is that we're measuring when we say that it can measure pulses down to 5 microseconds, what's happening is that the meter is showing the peak sum of all the radio frequency energy that was measured in that 5 microsecond window. Okay, so this meter, the Safe and Sound Pro 2, is got a sample frequency of 200 kilohertz. Okay, so that's 200,000 times a second the meter is listening to what's going on. So to give a rough graphical representation of what I'm talking about, I set the signal generator to generate a 100 kilohertz 50% duty cycle square wave. Now, it's beyond the scope of this video to get into sampling frequency and Nyquist frequency. That maybe can be for another channel or another subject. But what I want to show here, the reason I generated this is, think of it's a graphical representation of, think of it as each time you see this white blotch or this yellow blotch, that is when the meter is actually able to listen to what's going on. So anything that happens in this window is going to get stored by the meter and totaled up. And so the meter will show the peak value, what happened in this time. Now keep in mind, again, these are very narrow time windows. A lot of digital information and overlapping signals are much wider than that. So in other words, you know, they would be 10, 20, maybe 100 times wider. So what happens is, if there's a digital signal that's much wider than all these samples, we're going to get multiple samples to measure. And if we get 1 or 2 samples that line up with an RF event, we're going to get a very accurate reading. Okay, so that's why it's really important. In the case of smart meters, for example, smart meters don't transmit often, but when they do, it's a very short, narrow pulse. The packets are very minimal, and there are many RF meters on the market that are just incapable of measuring narrow pulses. They'll measure something, but they won't give the true value of what's going on. So our idea is to have the sampling frequency as high as possible, so that we can measure the narrowest pulses possible, as I've demonstrated in the video, that we can, in fact, we specify 5 microseconds, but we can go down to 3 microseconds. So I hope this gives you an understanding of what happens. Again, the sampling windows, and why having more smaller sampling windows is better for accuracy. So that you can measure both narrow pulses and wider pulses with the greatest accuracy possible.